Hello students. In this session, in this particular series, we'll look into linear regression. Linear regression, as you can see it on the screen, is a very notorious and famous element of machine learning in which using regression techniques, we can predict a numerical value. That is, I'm not talking about predicting a value in the future, but based on certain independent variables. There's a dependent variable, and that dependent variable's value can be predicted by forming an equation between the independent variables and the dependent variables. So that's what we're going to see. In this, we'll look into a data, as you can see it on the screen, that this data is of AIR BNB, and this is somewhere around close to, if I'm not wrong, yeah, around 74,000 data points of all the room types. What kind of rooms do we have? These are all 74,000 properties, listed properties on AIRBNB, and along with their price. Right now, the actual price is not mentioned, is the logarithm of the price, so that the number delta is slightly smaller. We can change that, but I think we can keep it to log price. What we're looking at is, we're looking at the ID of registration, which obviously doesn't mean anything. Room type, it does mean a lot of things. How many does it accommodate? How many bathrooms does it have? What is the cancellation policy? Is it very strict, or is it moderate or flexible? Right? Is cleaning fee applicable? If true, which means that you just pay separate cleaning fee. False, which means that it is included in the fees charged. Instant bookable, is it instantly bookable on the property? Or if it is false, which means that you need to book the property in advance. Review scores rating, what is the review score rating out of, let's say, appears to be 100%, right? And we can look at the number of bedrooms it has and number of beds in total it accommodates, and finally the price. So a target variable over here is the price. In the previous session, in which we have seen the customer segmentation, we have seen an ML technique in which there was no target at all. What we did was to segment the customer. We did customer segmentation over here. There was no target. Such kind of methods are called as unsupervised learning methods. Here we are looking at supervised learning method because we do have a target variable over here in terms of log price. Okay. So let's first understand what do you mean by logistic regression and how it works, and then we'll move on to the hands of it. Okay, hands on of this particular thing, right? So let me move on to, yeah, I'll minimize this Excel. I just wanted to show the data. In fact, before minimizing the Excel, I'll remove this this top row over here because this doesn't add to the data. So I'll just delete this. Fair enough. I'll just save this, and now I can close this. Now let's try and understand what do you mean by linear regression. Let's say I have two variables over here. I'll just put it up over here. Linear regression. Okay, this is what we are studying. Now, let's say there are two variables. One is, of course, this is, let's say, price only. I think we are already taking price. So there's a price, and let's say the number of bedrooms it has. Let's say, or probably review score rating is a better case, right? So review score. A lot of us probably will believe that as the review score keeps on increasing, the price keeps on increasing. Again, the probability is in your favor. That's probably, it is correct, but data might suggest otherwise. So just be ready for that. Okay, so I don't know whether the price is absolutely positively correlated to review score or not. But what regression does is, ultimate aim of regression is to find a best fit line over here. A line which is also called as best fit line. We'll see why is it called best fit line, which is also called as line of regression or regression line. Now with this, if somebody gives me, using this, what I've done is, I can, based on certain score, let's say the score starts from 20, it is, let's say, up to 80. I can easily predict, for example, if you give me 78 as the score, then I can say that, okay, perhaps the price of the property that we're looking at is this thing. So line of regression actually helps us to predict the price of the property at various points. And this is the example of the data that we are about to take, but it can be anything. It can give you, let's say, you want to regress the population of a certain city based on, let's say, population of a certain city based on the area the city has. So you have the data of, let's say, 10,000 cities across the globe, and if you look at the population, you plot the population on y-axis and the area on x-axis, you get a point. Okay, so all these are the points over here. The points better like this. I think the, it is going like this. Now what regression does is it finds a line somewhere. I'm so sorry, I think the line is not drawn properly, but let me draw some points over here so that I can make up for my mistake. Right, so the point is, the line of regression is that particular line which is helping us predict the population of a certain city based on a certain area point over here. Now you can give me an area point over outside this range. Perhaps let's say this is the area in which I can extend this line, and I can still see if this is the area, what would be the population of that particular city. So point is, using this I can form a relation between area and the population. This is called as linear regression. We're always after something called as best fit line or regression line. We'll understand how do we do that, how do we exactly get the best fit line, and how do we do this, because a lot of points are drawn over here, isn't it? But moving on for pictorial to more mathematical setup, we can say that, let's say the linear equation, let's say there is a variable over here. Y is my dependent variable, and let's say the independent variable is x. For example, y is my population and independent area variable is area. Then I think there is a very simple linear equation over here, y is equal to mx plus c, which indicates that there is a relation between x and y, and the relation is linear. That is one of the assumption of linear regression, that the relation between my independent variables, which is my independent variable in this case, one singular variable, and my dependent variable is linear. This is called as simple regression. It's a simple regression in which a dependent variable is depending upon one of the independent variables. But let's say there are many variables. For example, population not only depends upon the area, population depends upon, let's say, the happiness quotient of that particular country as well. Let's say, I'm just taking one simple example. It depends upon happiness quotient. It depends upon how many industries, how number of industries, or number of employment opportunities which are there, right? And what kind of government it is, all that kind of, what kind of country does it lie in. There might be many factors which might govern the population of a certain city, which means that it need not to be a simple linear equation. The population can be something like this, that m1 x1 plus m2 x2 plus m3 x3 and so on, and finally a constant, which means that x1 is the first independent variable. In fact, x1, x2 and x3 over here are nothing but my independent variables. Something like number of employment opportunities, the country, the happiness quotient, the area of that particular city, all of them are nothing but your your independent variables, where population over here is my dependent variable. Now idea is to get a line like this, the best fit line. This is the equation of the best fit line, let's say, right? So I want an equation something like this. What I want is nothing but the values of the coefficient over here. For example, if I get the values of the coefficient, let me take it very simply, right? Population is nothing but, let's say, 2.3 times area. Let's say there is a coefficient of 2.3 minus there's a coefficient of or plus 2.1 times happiness quotient HQ minus 3 times the number of employment opportunities. I'm just taking 3.7, let's say, plus a constant, let's say 23.4. Now this comes out to be a linear equation between these independent variable and the dependent variable. Now I can put in the respective values of areas, happiness quotient and number of employment opportunities, and I can probably predict the population over here, or population in million, let's say, right? So that's the entire point. Now if I get this equation, my job will be done. I can just keep on putting the values of independent variables and get the value of dependent variable. Now, how do we get to this such an equation? How do we get to such an equation is the question. Okay, so let me move on. Let me see what I can do. Let me create some space over here. Oops, probably this is not how we do it. Let me try and oops. Just a minute. I'll just put this down. Right, there we go. Cool. Now, the entire point is how do we get this particular equation with us? How do we get this equation? Right. So, let me take up an example. Let me take up a simple screenshot of the data that we have seen. All right, here it is. I think let me magnify the screen a bit. Yeah, there we go. Let me do it now. Okay. Now, let's do it over here. Now, if you look at the data here, how linear regression functions is, it calculates something called as correlation coefficient between values over here. Let's see. What do you mean by this? Now, first of all, correlation coefficient, which is denoted by R, is basically, let me decrease the thickness a bit, and then probably I'll come back when I scale down. Now, it's nothing but equal to the formula for Pearson's coefficient relation is very simple. It is sigma of xi minus x bar into yi minus y bar divided by square root of sigma xi minus x bar whole square, okay, multiplied by sigma of yi minus y bar whole square. Okay, that's the case. Now, this is the coefficient of correlation. It simply says that if coefficient of correlation is, if this coefficient of correlation, it says if it is equal to 1, the two quantities are positively correlated, which means that if a change happens, if x and y have a correlation coefficient of 1, if x in, let's say y is the independent variable, if y is the dependent variable, if x increases, y also increases to the same extent, right? And r is equal to minus 1 indicates that if x increases, y decreases to the same extent, which means that the extent of change will be same, but the direction of change will be completely different. That's the meaning over here. So r is equal to 1, it's positively correlated. So it increases by 30%, the other one also increases by 30%. Or if this increases by 50%, this also increases by 50%. A very, very ideal scenario. Generally doesn't happen in practical world, right? And r is equal to 0 simply means that there is no correlation. There is no correlation at all between the two variables over here. And how does it measure it? It measures by calculating the distance of x from its mean and y from its mean, and then putting this in the denominator over here. All right. So the point is, if we get the correlation coefficient, we understand that is there a relation between the two variables that we are seeking. And as we know that the variable that we are seeking over here is log price. It's just a sample of the data, as we have already seen that the sample consists of around 74,000 entries. But if you look at the log price, which is my y, so if I go for LP log price, and if I go for, let's say, the review score rating, okay, so review score rating. So if I just look at it, for example, 5.01, 5.12, 4.97 are my consecutive values, and 193, 92, 193 and 92. Now what it does is it assumes one of them to be x, right? This is my x and this is my y. Okay, and using this particular formula over here, which is calculating the mean of x bar, calculating the mean of y, which is y bar, it calculates the coefficient of correlation over here. What? The linear regression model calculate the correlation coefficient over here and finds out, and it does it for all the variable. By the way, this kind of linear regression model in which I include more than one variable, more than one independent variable, is called as multiple linear regression. So we just enter into multiple linear regression. Simple linear regression is just one independent variable and one dependent variable. Here it will be many independent variables contributing to one dependent variable, the target variable over here. Hai? So log price comes out to be my target variable. What I'm looking at right now is that all the variables which are contributing to this price, वो सारे variables जो इस particular price पे contribute करते हैं, we can just see it over here. Okay. Now, अब अगर हम आगे बढ़ते हैं, let's say if I just look into this too, what linear regression does is वो beds और log price के बीच का correlation coefficient calculate करता है. It calculates the correlation coefficient between every pair of the dependent variable with my every pair of the independent variable and the dependent variable, and based on the correlation coefficient, if it is very close to 0, obviously there is no correlation at all. So y doesn't change with the change in x, simply it means that way, right? Now if there is, depending upon what this correlation is obtained, it assigns the coefficient over there. That is how the coefficients are designed, and that is how the equations are designed. Or probably, as at this point of time, it helps us to determine which of them is the most, is or are the most important variable, right? Now based on the correlation, I get which variables are more important over here than the other one. Okay, so after all this is done, obviously the next thing that we look at is nothing but, yeah, I think we can do it now. The next thing is, of course, how do we get the line? Okay, now how do we get that particular line, the best fit line? So let me draw it over here. Now based on whatever the value of independent and dependent variables are, right, these are all the points related to, let's say, my review scores and the price of the property over here. Okay, these are all the points that we have. Okay, these are all the points. Now problem is, there are multiple lines which can be drawn going through these lines. Can I say this? There are multiple lines which can be drawn. Right, let me take up a line over here. Let me try and draw a line properly. I hope we can draw a line over here. Let's see whether we are able to draw a line. Let me see. Oh, it's a ray, but I think let's keep it as it is. I think that's fine. Right, so let's say this is the line. Forget about the arrow over here, doesn't carry an arrow, but I mean, arrow indicates a direction, but there is no direction over here. So this is the line that we are looking at. Okay, now how do we calculate the line which is the best fit line over here? We calculate the errors, right? How do we calculate this? We calculate the errors over here. For example, if you look at let me magnify this, or probably what I'll do is I'll just reduce the number of points present on this chart. Okay, so this is my line, and I'll just for the time being consider 2 or 3 points over here, right, for that, so that we can explain it. Something like this. Let me take up a point like this. Let me take up a point like this. Let me take up a point over here, and let's say over here. Right, now if you look at it, this is my value for, this is my predicted or regressed value of y, and this is my actual y. Can I say this? This is my regressed y, and this is my actual y. Now what is the gap over here? The gap is nothing but the error in prediction. Can I say this? Right, this is the actual value of the variable. As far as my best fit line, this came out to be the value of the variable as far as my regression line is concerned. Can I say this is my error? So can I say, if I say y hat is the prediction over here and y is the actual value, I can say that y hat minus y or y minus y hat is the error. Or I should say, at this point of time, it doesn't matter for me whether error is in single direction or multiple direction. Right, we can just say that. Let me take up a different color over here. We can see that now for this particular point, the error is very less. The error over here for this particular point is very less. Now if I look at the other point here, right, if you look at the other point, let me take up a different color. This is another error over here. Now the error is in a different direction. Now error is error, that is, error is just how deviated the actual value is as far as the regressed value is concerned. So वो error ऊपर की ओर हो या नीचे की ओर हो, it almost doesn't matter to me. So what I do is, I intend to do is to take a modulus over here, but it basically does something else. Linear regression model, what it does is, I'll come back to the original color of writing. What it does is, it takes the square of this, that is y minus y hat, that is the actual value minus predicted value. It takes the square of it. It takes the square of it, and again the squaring gives you two advantages basically. One, it gets rid of the sign first of all. I don't now worry about what is the error, and it very quickly, as we have seen in the previous sessions, it punishes the points which are lying away over here. So if the regression line is far away over here from a point, the distance will be high and the square of the distance will be higher, which means that, let's say if there are two distances, let's say this point is having a distance of, let's say 2.6, and the other one is having a distance of, let's say 1.7. Now if I calculate the square of 2.6, it comes out to be, if I'm not wrong, 6.76, and if I consider the square of it, it is 2.89. Now somebody might say that, okay, the distance is just 0.9 over here, the gap between these 2 points is just 0.9, it's not that significant, but the square makes that particular gap slightly more significant, which means that I end up punishing the point which is far away from a regression line. In a way, I end up punishing the model. मैं मॉडल को पनिश कर देता हूं जब मैं स्क्वायर कर देता हूं. तो स्क्वायर करने से जो पॉइंट लाइन से काफी दूर है वो उसका स्क्वायर और ज्यादा बढ़ाता है और तेजी से बढ़ जाता है, एंड हेंस दिस summation of all the square of the errors will become exponentially high, right? And it's just a mathematical way of ensuring that the model sticks to its best possible case, because if the points are deviating far away from the line, the error will keep on increasing very fast. Okay, so this is called as, let me call this error. People have different definitions over here, don't worry about the definitions. People have MAPE, people have MA, बहुत सारे हैं इसका भाई. This is basically square of the deviation over here, or as I would call it, variance between the actual value and the predicted value. Okay, now once I have this, now there'll be a line like this, there might be another line like this, there might be another line like this. Okay, now I can say that, let me get rid of this, I don't want a shape over here. Now if I look at all the 3 points, all the 4 points over here, I can say that the error over here is, let me take up a red pen again, it is right, the error is this much. Error got reduced for this particular line, but again the error got reduced over here as well. The error also got reduced over here and also got reduced over here. So I can say for this particular line, if you look at the error will still remain sigma of y minus y hat whole square. But I can say that for this line, the error will be slightly reduced because cumulatively the distances between the points and the line over here is coming down. Now there's only one line in which the error will get minimized. Wherever this error gets minimized, that leads to something called as best fit line. And in order to find the best fit line, what I need are nothing but the values of, if I just remind you of the equation is m1x1 plus m2x2 plus m3x3 and so on like this, and a constant. Okay, now we'll talk about the constant is my intercept. Okay, now if I look at it, m1x1, now what I want over here is, the way I will be able to define this line completely, will be able to find the values of m1, m2, m3, m4. That is, if I'm able to find the coefficients associated with each and every independent variable, I end up finding the line, and hence I end up finding the the best fit line over here. So the best fit line is the one. So for every line, the model is going to calculate the sum of errors. A computer can do it. You will take a lot of time to do that. But a program, right, a computer can do that easily. Now once we do this, once we look at all the errors for all the lines, the line in which the error is getting minimized comes out to be my best fit line. This is the line which is my best fit line. Simple as that. Once we get that line, we get the equation. Now for various values of x1, x2, x3, x4, x5, I can easily calculate the value of the dependent variable, which is my price of the property, isn't it? That's the entire thing that we're going to do with hands-on. Let's see this. Okay, now let's look at all the libraries that I need for doing my hands-on. Now, Numpy, Pandas, of course, these are the two libraries which are required. Then we have Seaborn for in case of any visualization requirement. We have Scikit-Learn.linear model. Through Scikit-Learn library.linear model library, we import something called as linear regression. This is that particular library which will help us build our linear regression model. Okay. Now, from Scikit-Learn, we also need to import something called as matrices, because it's very important for us to understand that have we built the right model or not? For that, we need to calculate certain matrices. Again, Scikit-Learn library helps us do that. Matplotlib is if we need to, well, plot something. Right, same as Seaborn over here. I'll run this code, and now I can see that the code is taking some time to run. This is embarrassing, but no worries. Finally, it has run. Okay, now let me start with this thing. Let me go for importing. Oops. Importing the data. Right, so I'll say that this is not my code. This is my markdown. Run this. This becomes. Whoa. This is my markdown, and this becomes my data. Now I'm importing the data over here. Perhaps it's too much. Right, I'll go for another hashtag, reducing the font over here. So importing the data, let me import the data. Now I can easily see that we have already done it previously. We'll go for read, and the moment I hit tab button, I'll get everything that I need. And I'll go for the codes closed. I'll go for AI, and I think it should give me, okay, it's not giving me, I think AIR BNB. Let me go for R. Yeah, got it. So AIR BNB is the one. Right, now I'm reading this data set. So this is my data set over here. Right, it's giving me an error over here, but I think we can, oh sorry, this is a warning, not an error. But yeah, we can see 74,000, around 74,000 rows and 11 columns are there. Let's store this in one of the data frame called as df. All right, so I'll just do this, and now once I call for df.head, I can easily see the top 5 rows over here. All right, now next step would be to do a bit of EDA. Right, for those who do not know the meaning of EDA is exploratory data analytics. Okay. And what we are doing is we are exploring the data over here, which will help us to build our model slightly better. Even more important in classification. So once we move on to classification model building, we'll see how important it is. Okay. So first I'll go for df.shape. And if I look at it, as we have already seen, 74,111 and 11 columns are there. Now, the first thing probably it comes to me is probably I should drop the ID column, because it's simply, I mean, there's no point having the ID column. ID as a number, the model might count this as a numerical value, but ID we know has no connection with the target price or log price of the property. So we can just drop it using a particular function df.drop. Inside the parenthesis, inside the quotes, we can mention the name of the column, which is simply ID, and the axis from which I want to delete it. Right now I want to delete it from the column, and x is equal to 1 represent columns. Now if I do this, and if I just go for, let's say, this, and if I just look at df.head, now I can easily see that the ID column is no longer there. Okay, let me move on to df.info. Okay, df.info, and then we can look into that. When we are looking at the information about each and every column over here, how many non-null values are present, and we can see that as the total shape of the data was 74,111, we can see a lot of cases are there in which there are not 74,111 data points present, which means that null values are present in all these columns. We can see the data type of each and every column. For example, rune type being a string data type is being represented by an object data type over here. Similarly, for cancellation policy, for cleaning fee, and instant bookable. Rest of them are float data points over here, which are, well, numeric data points. The next thing that we look into it is we try and describe the entire function over here. I think that's, let me call it describe. What it does is actually it summarizes the entire chart over here, in fact entire data over here, right? df.describe.t is going to give me something like this. Fair enough. I think yeah, we can do this, but I think we can see a lot of decimals over here, for which we can use a function called as round, and I think we can round up all the values to 2 decimal places. That eases up things over here, and we can also save it as data, or I can say df underscore summary. We can go for df underscore summary, and we can go for df underscore summary. Now this is my describe. Now you can easily see a lot of things over here. For example, if I look at the review score rating, it's a nice observation that the standard deviation is not big as compared to the mean, which means that the review score rating will be confined to a certain zone, which makes sense because I don't think the customers will be rating any property very, very badly, like 10 or 15 out of 100. The maximum range will lie between 60 and 90, 9500 over there as well. So if the standard deviation is around lesser as compared to the mean, I'm not that surprised. And if you look at the log price again, that is why the price is also not deviating a lot from the mean over here, right? That's a good point over here. Cool. So this is what a DF summary can do. We can just summarize this and can learn this. We are anyways going to do this for every model that we're going to build over here. Now, let me go for understanding the unique value for each and every variable. What I'll do is I'll call it unique values. Okay, I'll go for unique values. I'll say that this is not my code, this is my markdown. I'll run this and I'll run a pre-written code which says that for column in df.columns, if the data type of those columns is equal to object, then print that column in the upper variable. Like, I mean, for example, if it is accommodates, it'll be capital of all the letters over here, nothing much. And the number of unique types it has. For example, accommodates will have, I believe, 3 unique types: entire, home, apartment, private, and shared, if I recall this data properly, right? So the number of unique will be 3, and value counts will be nothing but the value of each and every unique value over here. Let me run this. Okay, now once you run this and see that the room type is 3, right? And then we have shared room 2163, private room 30,635, and entire home apartment is equal to this thing. Room type something dash means that there might be null values present over there as well. Now we have something called as cancellation policy. We can see that there are around 19,000 properties listed which have moderate cancellation policy, 22,000 all flexible policies over here, and around 32 have strict cancellation policies. Similarly, for cleaning fee, around 19,700 properties out of 74,000 doesn't charge for cleaning fee, whereas around 54,000 do charge for a cleaning fee. And similarly, for instant bookable T and F over here. Okay. Now, let me go for converting D and F into. I think I don't like this, so I'll just write this. Go for df dot df instant bookable. I'll go for quote over here. What I'm trying to do is F and T. I'm trying to convert this into this thing, false and true, right? So I'll just go for this, replace, and I'll say that let's give a list over here. The list is something like this: F and T, and this is equal to, right, false and true. Okay, this is equal to false and true, and let's replace in place is equal to true. Okay, so if I do this, the df now will have something like this, that this is now false and true. Looks slightly better. Okay, I should have gone for df dot head, but that is okay. Right, now let me do one thing. Let me try and find out, or I think there's something else as well. I think we can now look at the categorical variable and can think about treating the categorical variables properly over here. Okay, let's do that. Now if I look at it, the categorical variables are room type, cancellation policy, instant bookable, and cleaning fee. There's something called as a function called as get dummies. What it does is it gives you dummy value for each and every type of variable over here. Let me apply the formula. Let me get the case over here. I'll go for df is equal to pd dot get underscore dummies. Okay, get dummies, we have df, and then we have columns. Okay, df dot columns, and the columns we're looking at is room type. Let me copy it from here only. I think that way we avoid the spelling error, if any. Okay, then comma, I think there are 3 over here, or probably 4. So I'll go for cancellation policy, and I'll go for cleaning fee, and instant bookable. What I'm trying to do over here is to get the dummy values over here. Okay, and what I'll do is, once I do this, these are the column, I'll go for drop first is equal to false. Drop first will say that or drop first will avoid dropping that particular value over here, as we know, right? What it does is, let me tell you, once I run this code, I think will be in a better way to basically, will be in a better position to look at it. Okay, let me run this. And now once we run this, and now let's look at df. Now once we look at df, you can see that room type entire home apartment. So the entire room type is into 3 things over here: entire home apartment, room type private room type shared room. Point over here is that if you look at it, all the 3 types of room are being split into 3 columns over here. Okay, are being split into 3 columns over here. Right, and yeah, and we have cancellation policy flexible, moderate, and strict for all 3 of them. We have 3 room types, fair enough. We have 3 cancellation policies over here, and we have 3 cleaning fees over here, false and true. I think cleaning fee true or cleaning fee false can be dropped because it can just give us 0 and 1, but it doesn't matter much. So instant bookable false, instant bookable true, it's fair enough over here. All I need to do now is to replace true by 1 and false by 0. Let's do that. All right, so now let me replace the case over here just like we have done it previously. We'll go for replace, we'll go for, let's say, true and false, and this list to be replaced by this list of 1 and, sorry, not 9, 0. And I'll say that in place is equal to true. Okay, in place will become equal to true, which means that make this change permanent in df. So once I run this, and if I run df.head, I can easily see that now all the quantities over here which were either true or false previously is now either converted into 1 and 0. One more thing over here, as cleaning fee is having only 2 values, either true or false, right? But if I look at it properly, if I look at it over here, I don't think we require 2 columns here, because cleaning fee 0 and 1, these are all complementary. In fact, I'll just remove the head over here so that way you can have a look into it. If you look at 1 0 1 0 1 0 1 0, oh sorry, not over here, here. So 1 0 1 0, and then we have sorry, 0 1 0 1 0 1, then we have 1 0. So these two are complementary. So is it saying that is cleaning fee there? It says no, 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 yes. And the point is the other column is saying just the opposite of it. So I don't think we require both the columns over here, and same goes for instant bookable false. So what I'll do is I'll drop these 2 columns. I'll drop these 2 columns, which is, again, I'll give a list over here. The list is cleaning fee false. Okay, cleaning fee false, and instant bookable false. Right, we'll drop these 2, and what we'll do is we just need to say that access is equal to 1. Okay, and we have in place is equal to true, which will mean that the changes will be permanent in the data. I'll do this, and if I have a look at my df now, I'll go for the same thing, df.head, and let me run this. Now we can see that there's only one cleaning fee true and instant bookable true, right? We can do this. I think this is fine with us now. Now the next thing that we are going to go for is, which I'm really very interested in getting into, is called as null value treatment. Okay, so let me look into it. Let me look at the null value over here. Okay, now once we go for this, I think the first function that we use is df dot is null, right, is null dot sum. This is going to sum up the null values of each and every column. If I go for another sum value over here, it's going to sum up the values for each and every column as well. So it's going to give me the totality over here. That is total sum of values over here. What happened? What went wrong here? Is null dot sum, is null dot sum. I think it's absolutely correct. Oh, forgot the parenthesis here, right? So it'll be 17,151. A total these many values are missing. Okay, now we can do one thing. What we can do is we can, in fact, remove the last sum and see that how many duplicate values are there in each and every column. And we see that the review score rating have a lot of duplicate values over here, right? Around 16,722. In fact, all of them, cancellation policy, moderate, all of them have almost no missing values over here. That is good for us, right? So what we can do now is to look into this and can replace this null values with something that is called as null value treatment over here now, and that is called as actually imputing the null values. In fact, null value in itself is a subject to study, right? I'll probably make a separate video on this, and we will talk about how should we treat the null values, how should we observe the data, and how should we treat the null values, what kind of treatment null values go for. Okay, as of now, I'm going to go for very easy treatment over here with the free and pre-written code, that is this one, which says that again, for column in df.columns, df column dot data types, if it is not equal to object, if it is not equal to object means I'm talking about all the numerical columns over here. It says that if you find a column of df.column as a numerical column, calculate the mean of that column using this particular function df column dot mean, and store it in one of the variables called as mean. Now then replace the column with a function called as fill na. Now the function or the objective of this function is to only the fill value. It will not touch the value which is already present in the column. It will only treat the null value and it will replace the null value. It will fill the null value with the mean of that column. Okay, and this is going to happen for each and every column where the data type is not object, in this case float, which seems to be the first 5 columns over here. Okay, so let me do this, and now once this is done, we can now see that there is hardly any null value present in the data, and we can now proceed to bigger things. Okay, now what we can go for is, I think we have already seen summary. Have we seen the summary over here? Yes, we have already seen the summary. And now we can go for something called as checking for duplicates. I think that is something we should do. Duplicates. Okay, we'll not spend a lot of time on EDA in this case because our objective in this session is to build a linear regression model, so we'll move on to that very quickly. Okay, now just let's do one thing, df dot duplicated. I'll just run this and we'll see that, okay, I'll just go for df.duplicated.sum. Forgot the sum. Sum is going to give me the total. Oh, and then there are duplicate rows present over here, 19,994. We have no other choice but to drop these duplicated rows. These are all the same rows, which means that a property might have been listed more than once in the data point, or it's been counted more than once in the data set. What we need to do is to drop underscore duplicates, right, and we'll go for in place is equal to true. Okay, we'll go for in place is equal to true. Oops. right? And now if you look at df dot shape, which is going to give me the number of rows and number of columns, we would have removed all the duplicated values, and it's giving me 14 columns over here. Fair enough, I think it's okay, it's cool, right? So that's the point. This is it. Now we are ready with our data, and we can now proceed with whatever we want to do over here. Okay, now let's move on to a bit of bivariate analysis over here. If you look at the bivariate analysis, it's going to give me the relation between the variables. And before I build my model, bivariate analysis is important. The first thing that we're going to go for is to go for a correlation map over here. So let me go for this thing, sns dot heat map, and I'll go for, in fact, df.core. All right, and let me go for this. This is the case over here. This is what we are looking at now. This simply means it is giving me a relation between the each and every variable. It's correlation. Now, before I move on to this, let me use a better space over here. So I'll go for plt dot figure, and I think this is, go for fig size is equal to, I think 15 and 10. Let me try this one. I just want to, yeah, I think it's better, isn't it? It's better that I can see the graph slightly better. Now we can see that all the variables are there on y-axis, and the same variables are there in the x-axis. It's giving me the pair of every variable with every other variable. So it's giving me the correlation. Now the each and every square that you can see over here is giving me the correlation between a variable and the rest of the variable, right? And it gives me the scale of the correlation. For example, if the scale is like -1 over here, the darkest, to the lightest over here. Now the darkest to lightest would simply, darkest would mean -1, which means that the correlation is -1. A change in one of them will bring about the same kind of change in the other one in opposite direction. Okay, and here the light color indicates that there is a correlation of 1, which means that a change in one quantity brings about the similar kind of change in the other one. We can see a lot of light variables over here, and we can see a lot of dark variables over here. But the only thing that you should be looking at right now is there is a diagonal over here which is giving me the lightest color, because it is accommodates versus accommodates. So accommodates and accommodates, obviously the correlation will come out to be 1 because the variable is same. Now you can look at either the upper part of the diagonal or the lower part of the diagonal, because the pairs are getting repeated in this particular part. However, I can just make a note over here, and I'll go for a not is equal to, if I'm not making any spell error, a not is equal to true. And I don't think it's, and I'll say that let's put the annotation over here as true as well. For some reason it's not giving me the annotation over here for all the variables. I think this is a problem which has happened with me since some time now. We'll look into why is this happening, but no worries. As you can see, the numbers are being reflected on top row. The same number is reflected across the entire this thing. Now if I just look into it, can I just show you how a heat map, correlation heat map, we call it correlation heat map. I'll just want to show you certain images here. If I can show you the images, I think even that would just, yeah, something like this, right? As you can see, the numbers are being represented over here because of some settings in my Python file. I think all the numbers are not coming up, only the first row is coming up, but the numbers over here are the representative of the correlation that we have. Now we can easily, I think it's better to look at log price and which particular variable has a good correlation with log price. We can see that log price has a lot of significant correlation with other variables because a lot of light colors are being covered up over here, which means that it's going to give me a good understanding of the model, and I think I can start building my model as well. Alright, so before we proceed further now, the next concept that we need to look into is model building. Now we are getting into the real model building of linear regression. Okay, so I'll just make this. The first concept that we need to understand is test train split. We split the entire data into various portions over here, 4 to be precise, and all those portions have a certain certain purpose to be solved over here. Let's see what that is. So I'll take you guys to the dashboard over here. And where is my dashboard? Where is it? I probably will have closed it, but no worries. All right, now, so let's look at the test train split. So what happens is, if I adjust, let me put up a shape over here. I think, yeah, I think this is a good shape to go for. Let's say this is my entire data. Okay. And in this entire data, we have, let me put up a line. All right, let me use a pen over here only for the same. Now what happens is, this is all my data. There are many independent variables over here. For example, let's say x1, x2, x3 till let's say xn. These are all the independent variables, and there's a dependent variable y. We need the equation of y in terms of x1, x2, x3, x4, right? So what we do is, what test train split does is, it splits the entire data into two portions, two unequal portions, something like this, right? So I have drawn a line over here. Now what it does is, it splits the entire data into two portions. First portion is called as train. The other one is called as test. As the name indicates, what we're going to do with this data is, basically we're going to train our model using this particular data, and then we're going to test that model on this particular data. Now this data over here, which I'm about to plot, this data over here is actually unseen data by the model. That is why this is also called as unseen data, right? Because I'm going to build my model based on this train data. Now, once we split the data into train data, then the next step that we do is, we split the data vertically as well, right? So now let me change the color a bit so that we can easily identify it slightly better. Probably blue is better, right? So what we do is, we draw a vertical line over here, and what do we split? We split the independent variable. We split away the independent variables and the target variables. So as there is a horizontal line which is divided train and test data, generally the train and test data are divided. Generally the train and test data is something like 70% of the data is train data and 30% of the data is test data, but is just a convention, right? It's not a rule over here. It might be 75, 25, 80, 20 as well. Okay. So you can make it 80% of the train data and 20% test data as well, but it's up to the data analyst over here. Now once we divide it, now as there were only two portions before, now because of this vertical line, the entire data got split into four portions. The first portion over here, the top left quadrant, is called as X train. It's called as X train. This is a set of all the independent variables in the train portion of the data. This is called as Y train, and this is nothing but the set of the dependent variable, the target variable from the train data. So the train data got split into two parts as well, because of this vertical line, right? So X train data and Y train data. Now I'll feed the model X train and Y train values, so that the model can now learn the relationship between these two, can form a mathematical relation between this entire set of independent variable and this target variable. Now once that relationship is established and stored in the model, that is the model, the relationship is the model, right? So once we have that particular model in place, then we take that model and try it up over here. Now this data that we are seeing right now, let me rub off a few portion over here, this data over here, and if I can, I probably should change the color. Let me go for red. This is called as X test, right? And similarly, this is called as Y test, right? So X train, Y train, X test, Y test. X train and Y train is the data which is fed to the model, which is fit to the model. The model learns the relation between X train and Y train. The relationship is the model, or we can say the relationship got stored in the model. The model is then brought to the test data, which is also what? Our unseen data. The model has not seen this data before. Model has seen X train and Y train, not X test and Y test. Right? Now what happens is the model learning is there. Now what we do is let me do one thing. Okay, I'll just bring this down as well. Okay. And I'll just actually give you another screenshot in which we'll see the exact data. Okay, we'll take. All right, I think this is going to give us a good and a better idea, I guess. So this is my entire data. For the sake of simplicity, these are all 21 rows. And let's say I'll just take the example over here. Obviously, the example is having very small and small data set over here. But if I look at it, this, let's say, is the 70% of the data is also called as train data, and the rest of the data is test data. Okay, let me rub it off. I think I'm going to use it later on. Right, so this is my test data, the other portion over here. Yeah, test data. Now if I just look at it, if I just segregate out this is my target variable. If I just segregate this out, right, and this is that horizontal line which is dividing the test data and the train data. Now can you see this portion over here, which is from id till beds, over here, this particular portion is your X train. Okay, this particular portion of the prices, corresponding prices, are called as Y train. Clearly Y is nothing but an array over here. Now this is where the fun starts. Now the model is built, and now we move on to test data, and we feed the test data to the model to check how effective is my model. And now what happens is there are actual values present for these test variables, isn't it? There are actual values present. We calculate another set of values over here which are called as predicted value. Okay, now the model has learned the relationship, has formed the equation. Using that equation, and we feed the X test values over here. These are all the X test values. We feed it to the model, and let's say the model starts predicting the value. For example, let's say the first value is 4.12, the next value is 4.61, the next is 4.32, and so on like this. So on like this, the predicted values are coming up over here. And now this is my Y train, Y test, and this is my Y predict or predicted values of Y. Now we can compare the Y predict and Y test, and we can find out that how effective is our model building, because if I just calculate the error between the two, I'll have a better idea about have I built a good model or not, or is it a good model or not, right? So that's what we are going to do. That is the entire modus operandi of test frame split. Okay, let's see how it is done in Python. Now let's go move on to the hands-on. All right, so let's start with the Python file over here. The first thing that I'm going to do is to create X and Y, right? It's to create X and Y. X is a set of all the independent variables, which is done by df.drop. What do I drop? I drop the target variable over here, but I'm not doing it for this thing. I'll go for, let me go for log price. Is it reading it? Let me go for this. Okay, perhaps it's not reading it. Fine, I'll just write it up over here. I think log price is log underscore price. It's not coming up. No worries. So I'll go for log price. X is equal to df dot log price. Let me run this. Okay. I had to go for the axis over here. I'll have to define the axis. No, that I forgot. Axis is equal to 1. Okay. Once I do this, X is defined. Similarly, now Y will be nothing but equal to df, and that df is nothing but equal to your, in fact, there will be another set of square brackets over here, and this is my log price, right? This is my log price. This is Y, X and Y. X is df dot drop log price. Now if I just have a look at X dot head, you can have a look at it. This is X dot head, isn't it? This is X dot head, as you can see, there is no log price over here. All the variables over here are my independent variables, the x variables. Now similarly, if I have a look at y dot head, I think this function will not work over here. Oh, probably it worked. Great. So this is giving me log price over here. This is an array. That's why I thought that will probably not work, but it did work. So this is my log price over here. Okay. Now let's do one thing. Let's go for building the, or probably I'll have to go for test train split right now. I just given x and y separately. Independent and dependent variables are being separated. The only thing that I need to do now is to, you know, do the test train split. For that, what I need to do is again a pre-written code. This code is used plenty of time. From Scikit-Learn model selection, import train test split. Right, that's what we're going to do. This is the library which is going to split the data further for us. We have already split it up in x and y. It's going to split up in x train x test, y train y test as discussed, using a function called as test train split, and you have to give what you need to split. This is the set of all the x variables. This is set of all the y over here. I think we have got capital Y. I think I think it is capital Y. That is probably, I think I'll just avoid that. So I'll just run this. This is x dot head, this is y dot head. I think I'll just go for small y over here, as Python is case sensitive. Now here the test size is 0.25. This is 25% of your data is test data. You can always change it to 0.2 or 0.3. Right now the distribution is 75-25, and let's not worry about what this random state is, just a number over here. Although I need to ensure that the random state number seems absolutely is constant throughout the model building exercise. Now I run this and I can now see my x train. If you look at the x train, right, in fact x train will look absolutely like, well, x only, isn't it? It has the index here. It is looking like x only, but if you look at the x dot shape, right, and if I go for this, print x dot shape, right, and if I go for printing x train dot shape, right, we can easily see now 54,117 was the data point. 70% of that is around 40,587 is my x dot, I'm so sorry for this, is nothing but x train dot shape. And if we want to take it a step further, we can look at x test dot shape. Okay, and this is how it will be. We can see that y-axis, nothing has happened to the y-axis, nothing has happened to the y variable. It's just that the x variable, the number of rows got distributed. Similarly, I can just have a look at, the same thing for y. We can easily see y dot shape, right, and we can have y train dot shape, then we have y train dot now we can easily see that the same thing has happened over here. Okay, because it's the number of rows, it's the column is 1, because it's just the price column which is coming up, isn't it? Now my 4 parts are ready. What I need to do is to build a model and feed x train and y train, x train and y train data as we have discussed to that particular model. So let's build that model. Let me go for regression model, and let's call it regression model is nothing but equal to linear, right, regression, linear regression. Now once I define this, I can see that the linear regression model is defined now. What I need to do is in this regression model, regression underscore model, what we need to do is to fit my data over here. Fit my data of x train and y train. Okay. So x train and y train has to be fit over here so that the model starts learning. The moment I run this code, the model would have learned the relation between the x values and the y values over here. That is the independent variable and the dependent variable. Right. Okay, I think I made a mistake in, oops, sorry, there was an extra E over here. So now the model is defined. The model is there now. The only thing that is left to do now is to test this model. Let's do that. Okay. Now, before we start testing, we can just explore the model further. Probably you must be wondering, what is the equation? Where is the equation? I can't see the equation which is formed over here. For that, what we need to do is to calculate the coefficients over here. Okay. For example, if I just look into it, I think if I just call it a regression model, right, once the model is there, I can do anything now. Regression model dot coef, that is coefficient underscore, is going to give me all the coefficients one by one. This is an array of all the coefficients over here. So this is the coefficient of the first variable, this is the second variable, this is the coefficient of the third variable. Obviously we cannot always expect absolute integral coefficient, isn't it? So the coefficients mostly are in decimal format over here. We can always run a code over here to write down the coefficients in a better format. So I'll run this particular code. This code is going to give you all the coefficients over here, right? So I think this I used in the previous sessions, but yeah, as you can see, the coefficient for accommodates is this thing. The first one was accommodates, this is the coefficient over here. The coefficient for bathroom is this, the coefficient of review score rating is this. Everybody has a coefficient over here. It also has a constant term which is also called as intercept, right? So what we need to do is we can check out the intercept as well. For example, if I go for regression underscore model underscore intercept, that constant thing is nothing but my intercept. Why is it happening? Have I made a error somewhere? I think the model is clear, right? I think the regression model is the same, right? If yeah, it's the same. And acha, oh, I'm so sorry. It has to be dot intercept. I made, so sorry, my bad. Dot intercept, and I think it should be, yes, as it is turning blue, I think it is good. Now this is the intercept over here, 3.420. So if you really want the equation, I can write the equation now, something like this. Just a minute. Something like this. That is my log price. Log underscore price is equal to 0.074 times the accommodates plus 0.1555 times the bathroom, the number of bathrooms I should say, and so on like this for all coefficients, and finally an intercept of 3.42. Right, log price. This is the equation which you're talking about, right? This is the equation which is formed, right? Now let me remove this and move on, come back to the hands-on over here. Again, now comes in, okay, equation is fine, the equation is there in front of me. What can I do with it? Now, how do we know that the model is good? How do we know that's performing better in, trained data as well? What we need to do is we calculate the the score of this particular model. So this is basically model evaluation is what we are talking about. Okay, so model evaluation, markdown, this is my model evaluation, and the model evaluation now will talk about getting the score. The score is nothing but the the error over here, error percentage, right? What portion of the entire model can be explained by this? So let me see this. What I need to do is get me the regression underscore model, the model that we have built. I think this, so I think this is where what we need to do is to ensure that we don't use a lot of caps over here. Otherwise, Python is slightly it's actually case sensitive, right? So it might give me problems. Now, score, you have to feed score on what? So you tell them x underscore test, and then in fact what people do, what analysts generally do, what we do over here is x train and y train as well. See, understand what I'm doing. I'm actually calculating the score based on the data using which the model is made. Okay, so this should perform well. Now if I do this, the score comes out to be 50.35. Well, I must say slightly disappointing, right? I'm expecting better score. Let's see what happens with test data over here. So if I go for test data, X test and Y test. If I run this, I still have 50.51. That is, what do you mean by this score over here? What is the meaning of score over here? Okay, the score is, it's the meaning that, I'll just get the annotation in place, 50% of variation in price can be explained by the given independent variables. Right, can be explained by the given independent variable. That's the meaning over here. Okay, now let's say the score is well acceptable to me and I want to do, okay, what can I do now? You can predict the values over here now. Okay, so if I go for something like, let's say, let me predict the values. All right, so the code that I'm using over here is, I'll go for predicted values is nothing but equal to, right, now you need to tell regression model that, okay, fine, I think I have no other choice but to accept your score. So I'll just although I'm not very happy with it, but I'll still do it. Now regression model is the model that we have built, dot predict, and predict on what? Predict on x underscore test. Predict on x underscore test. If I run this, there are predicted values. So now we can run the predicted values over here, and this is the array of all the predicted values that the model has given you over here. Okay, so these are all the predicted values. Now you can compare this with your actual values as well, and of course that is how the score is obtained. So let's not do it again. Okay, so we can now actually calculate a lot of other matrices over here, and I think let's see them one by one. In fact, let's calculate only one. Let's not get too much into calculation stuff over here. The only thing that I want to calculate is that error thing that we mentioned. Remember, we talked about the error, the distance of, this is the best fit line that we just derived. Let's calculate the error over there. What is the error over here, right? So in case you guys have missed or probably are not able to recall what we discussed in the best fit line, the best fit line is something like this, and the points are lying somewhere over here, right? And what we are trying to do is to actually find out the error over here. What is the error? Error is nothing but the square of the distances that we have. This is the error over here. Now sum of squares of the distances. That is nothing but mean square error. Okay. Right, so let's do it. It's simple. I think we can have I think we have already predicted the values, which are my predicted values. What I'll do is I'll calculate this using a Numpy. I think I have a code written over here, so I'll just put it up. We'll calculate the square root of the matrices, and this is where the matrices dictionary is coming very handy over here. So mean squared error is going to give me the square of the error. Okay. Now if I don't take the square root of it, I'll get the mean square error. Now y test is the actual value over here, and the predicted test, or in this case we have not used something called as predicted test, will be using predicted values. Okay, so this is what we had. So predicted values and y test. So now we can calculate the error that has come up. Now if I look at the error comes out to be equal to 0.53. That is 0.53 is the mean square root error over here. Right, so this is mean squared error. Square root of that is square mean error over here. Okay, so that's the point. This is how linear regression models are built up. Now, as we can see, the model is not very effective or not very, the score is not great. The score is not very satisfactory. What we can go for is we need to go for better models over here. And that's when we'll go for better models like Lasso and Ridge in the next session, in which we'll talk about Lasso, Ridge, Stats model. Okay, let me talk about Lasso, Ridge, and Stats model in the next session. We'll stick to linear regression. Let's look into it and let's finish off linear regression in the last case. I'll try and include model deployment in the next session as well. All right, see you guys there.